Mathematics Analysis and Approaches, Paper 1, Time Zone 1, HL, May 2025. This is question number 12 and it carries 19 marks. This is the last question of the paper. He talks about a family of functions, f of x is equal to cos to the power of nx. And he wants us to integrate this by writing cos to the power of nx as cos to the power of n minus 1 into cos x. This can be done using integration by parts. And you will end up with this big equation here. Okay. And from there, I have to prove that the function written in this form is going to be f of n minus 2, which basically means that the cos to the power of n minus 2. And using this, I need to find out what is cos to the power of 4x. Once we identified this one, the next step is pretty simple, and the step after that is going to be just substitution in this equation. And that expression needs to be written in this form, which is again possible. Using that, I am going to be finding the integration of cos square x, right? Integration of cos square x either can be done using this big formula, or we can write cos square as 1 plus 2 cos 2 theta divided by 2. We can use the double angle formula. I can find the area of revolution, the volume of revolution, sorry, around the x-axis using the same formula. And here we're going to be applying Maclaurin series for the expansion of f of nx, and then finding the limit. All right. Here we can find the limit using the L'Hopital's rule. All right. That's pretty simple. Let's quickly start with the first part of the question. What I have is f of x as equal to cos to the power of nx. Of course, I can write this as cos to the power of n minus 1x into cos x. Here I'm going to consider u as equal to cos to the power of n minus 1x and dv as equal to cos x. The differentiation of u, which is du, is n minus 1 multiplied with cos to the power of n minus 2x into, I'm applying chain rule over here, so the differentiation of cos x is minus sin x. And the integration of cos x is simply sin x. So taking this back, I know that integration of u dv is u into v minus integral of v du. So I'm going to use that here. U dv is cos to the power of n minus 1x into sin x minus integral of v, which is sin x, into du, and du is going to be negative sin x multiplied with n minus 1 cos to the power of n minus, is going to be a n minus 2 x dx. Further, I can rearrange the terms into sin x plus n minus 1 is a constant, so I can take that out common, and this is going to be cos to the power of n minus 2x into sin square x dx. All right. Next, I can write this as cos to the power of n minus 1x into sin x plus n minus 1 integral cos to the power of n minus 2x. Sin square x can be written as 1 minus cos square x. Further, I can write this as cos to the power of n minus 1x into sin x plus n minus 1 integral. This when multiplied will give me cos to the power of n minus 2x minus cos to the power of n minus 2x into cos square x is simply going to be cos to the power of nx. So I can write this as minus cos to the power of nx dx. Going further, I can write this as cos to the power of n minus 1x into sin x plus n minus 1 multiplied with integral of cos to the power of n minus 2x minus dx minus n minus 1 integral of cos to the power of nx dx. Takes care of the first part of the proof. So that is basically what we have here. N minus 1 sin x, n minus 2, and n. All right. So if f of n is cos to the power of nx, then I can write this as f of n minus 2 and this also as f of n. So this is fnx dx is equal to cos to the power of n minus 1 x sin x plus n minus 1 integral of f of n minus 2 x dx minus n minus 1 and then integral of f of n x dx. To make things simpler, I'm going to take I as equal to integral of f of n x dx. And I can probably write this as in, and therefore in minus 2 will be integral of f of n minus 2 x dx. So when I go back here, I can write this as in as equal to cos to the power of n minus 1 x into sin x plus n minus 1 in minus 2 minus n minus 1 in. Now transposing in to the left hand side, I'll have in plus n minus 1 into in as equal to cos to the power of n minus 1 x into sin x plus n minus 1 into in minus 2. So here when I open up the bracket, I will have in plus in minus in. So you can see that these two will get cancelled. So on the LHS, I will simply have in as equal to cos to the power of n minus 1 x into sin x plus n minus 1 into in minus 2. So in can now be written as 1 over n cos to the power of n minus 1 x sin x plus n minus 1 by n in minus 2. So if I substitute the value for in, that is simply fnx dx is equal to 1 over n cos to the power of n minus 1 x sin x plus n minus 1 n, and this is integral of f of n minus 2 x dx. And that's the answer for part B. The question looks a bit scary. However, if you calm down and start doing your work, the things will fall in place and you will get the required terms that you have in these equations. Okay. At times it is easy to get anxiety the moment you look at these questions of this sort. All you need to do is take a deep breath and just start solving it. Okay. Right, great. So let's use that to find the integration of cos to the power of 4. So when I'm trying to integrate cos to the power of 4, I can either use the above formula or I can simply write cos to the power of 4 as cos square x the whole square dx, and then use the double angle formula, which is 1 plus cos 2x, right, whole square, and then apply a plus b the whole square in the numerator and then expand it again. You can substitute for cos square. That is one way of doing it. The second way of doing it is to use the conclusion that we got here. So if I'm going by that, I can write this as 1 over 4 cos cube x sin x plus 4 minus 1 is a 3 over 4 integral of cos to the power of 2 x dx. Right, I simply used whatever I got here, and this is what I ended up with. Again, here you can apply the cos 2 theta formula, or you can go back and reapply the conclusion that we got here. I'm going to try and apply the conclusion that we got here. So this is simply going to be equal to 1 over 4 plus 3 by 4 open parenthesis. I'm going to reapply the same formula that we got here. So it's a 1 over n, and that's a 1 over 2, and cos to the power of n minus 1. So that's a cos x and sin x. And then we will have n minus 1 by n, so 2 minus 1 by 2, so that's a 1 over 2. And I will have f of n minus 2, which means cos to the power of 2 minus 2 cos of 0, cos to the power of 0, which is a 1, so integral of 1 is simply a x, so this is simply a x plus the constant c. So if I open up the brackets, I will have cos cube x sin x plus 3 by 8 cos x sin x plus 3 by 8x plus the constant c. Let's quickly see if we got the same answer here. So that's p cos cube x, q cos x sin x, and rxn plus c. That is correct. All right. So we can move forward from here. So we can see that the p value is going to be 1 over 4, the q value 3 over 8, and then the r value is again a 3 over 8. For the next part of the question, he says that there is this graph, and this graph is cos square x. This is rotated along the x-axis. What I need to now find is the volume of the solid. This is simply going to be equal to integral of f of x the whole square dx, and of course there's going to be a pi outside. So the volume of solid is pi integral of f of x the whole square dx. Integration is going to be from minus pi by 2 to plus pi by 2. I can either continue writing the limit, or I can integrate the function completely and then apply the limit. Anything is fine. What I can also notice is that this entire function is symmetrical along the y-axis, and therefore I don't need to integrate from minus pi by 2 to plus pi by 2. I can integrate it from 0 to pi by 2. I'll get a particular volume, and that volume simply can be doubled. So here you can see that I have plotted that function on Desmos, and this is your cos square of x, right? And when that particular function is being rotated along the x-axis by 2 pi, then what you get is this kind of a shape, right? And that's the area that we are trying to find out. That's the volume we are trying to find out, not the area. Okay, so what I'm doing instead is to consider the area from 0 to a pi by 2. So when I consider the area from 0 to pi by 2, you can see that I'm getting half of the volume, or half of the solid, and I'm simply going to be multiplying it by 2 to get the complete volume. So this is going to be equal to integral pi integral of minus pi by 2 to plus pi by 2. This is going to be cos square x the whole square dx, and which can be written as pi integral from pi by 2 to minus pi by 2 to plus pi by 2 cos to the power of 4x dx. I'm going to take down what is cos to the power of 4 from what I derived here. This entire thing is cos to the power of 4. So in this, I'm going to be applying the limit from minus pi by 2 to plus pi by 2. Pi multiplied with this minus pi by 2 to plus pi by 2. I'm going to be a bit smart here. I'm not going to substitute the entire value. What I do know is when I substitute the upper limit, which is pi by 2, cos pi by 2 is going to be a 0, so this entire term is going to vanish. It is also going to vanish because cos pi by 2 is a 0, and what I'll remain with is only this much, so that's going to be 3 by 8 multiplied with pi by 2, and this is subtracted with, again, when I substitute minus pi by 2, this term is going to vanish. 0, this is also going to vanish because it's going to be a 0. This is what's going to remain, so that's a 3 by 8 into minus pi by 2. So this is further pi, open parenthesis, 3 pi by 16 plus 3 pi by 16, and that's going to be pi multiplied with 6 pi by 16, and that is 2 3s are 2 8s are, so 3 pi squared by 8. And that's the solution for the subpart where we are looking for the volume of the solid. So I'm done with part D. I'm looking at part E now. Now, what is Maclaurin's expansion or Maclaurin series? Any function f of x can be written as f of 0 plus f dash of 0 into x plus f double dash of 0 divided by 2 factorial into x square. He wants us to expand it only till the power of 2, and therefore I'm going to stop there. You can remember Maclaurin's expansion as this. F of x is going to be equal to summation of the function from n ranging from 0 to infinity, and this is going to be f of n of 0 divided by n factorial into x to the power of n. All right, so that's your Maclaurin's expansion. So what we have is f n of x, which is cos to the power of nx. So first let me find out what is cos f of 0, which is cos 0, and that's simply going to be a 1. Now let's differentiate this function. F dash of x is simply going to be equal to n cos to the power of n minus 1 x into minus sin x. So here, when I substitute 0, I'm going to have a 0, because sine 0 is going to be a 0, so the entire function is going to get multiplied with a 0. Let's double differentiate the function. So f dash of x is minus n sin x into cos to the power of n minus 1x. F double dash of x is going to be equal to minus n taken common out. I'm going to be applying u into v rule. So that's a u differentiation of v into minus sin x plus v. So I know that this entire thing is going to be a 0, because sine 0 is going to be a 0. So here I'll have a 1, because cos 0 is going to be a 1. So ultimately this is simply going to remain as a minus n into 0 plus 1, which is simply a minus n. So I can take these both and go back to the Maclaurin's expansion and say f of x is equal to f of 0 plus f dash of 0 into x plus f double dash of 0 divided by 2 factorial into x square. So I have f of 0 as 1 plus f dash of 0 as 0 plus minus n. So that is simply going to be equal to 1 minus n. We will have a x squared by 2 over here. So that's 1 minus of n x squared by 2. And that's your Maclaurin's expansion. Now let's look at the last part of the question. He wants us to find the limit of that. Limit as x tends to 0 minus 1 divided by x squared. Okay, so when I substitute the value for x is equal to 0, obviously the denominator is going to be a 0, so I won't be able to find the limit of this particular function. So I can go with the L'Hopital's rule, or I can use what I have here, Maclaurin series expansion, till the power of 2, and then I can probably find the limit. I think that's what I'm going to do. So this is going to be equal to limit x tends to 0, 1 minus n x squared by 2 minus 1 divided by x squared. So 1 and 1 will get cancelled. So I will have limit x tends to 0 minus n x squared by 2 divided by x squared. So x squared and x squared will get cancelled. So what you will remain with is limit x tends to 0 minus n by 2, and the solution is simply a minus n by 2, or the limit is simply going to be a minus n by 2. I think that is it for this question. Right, pretty lengthy one, though the working looks pretty lengthy. I have detailed the steps for you. So by practice, you will be able to write shorter steps, right? That is it for this video. Yeah, complete 19 marks question. Thank you and goodbye.